Welcome to the deep dive, where we really try to get to the heart of complex topics. Today, we're diving into something that honestly still feels like science fiction to me: superconductors.
It does have that quality, doesn't it?
Totally. I mean, get this. Imagine an electric current just flowing for almost 29 years, 28 years, 7 months, 27 days to be exact, with absolutely no power source keeping it going.
That actually happened
Yep.
in Belgium, right, in a
Yeah.
superconducting gravimeter. It's incredible.
Right. Or picture like a heavy sphere just hanging in midair, levitating, no strings, no visible support. It's wild.
And these, seemingly magical things are very real properties of superconductors. They're not just lab curiosities, though.
Okay, so that's our mission for this deep dive then, to explore these materials, figure out what they could do for us, what's holding them back.
Exactly. And then, crucially, how new approaches, things like materials informatics and artificial intelligence, are helping us find new, maybe more practical superconductors much faster than before.
All right, let's start at the beginning. For someone who's maybe heard the term but isn't sure, what is a superconductor fundamentally?
Well, it really boils down to two main things, two amazing phenomena. First, zero electrical resistance.
Zero. Like none at all.
Precisely. Think about a normal wire, like copper. Electrons flowing through bump into atoms, right?
Mm-hmm.
That creates friction, resistance, and wastes energy as heat. Your phone charger getting warm, that's why.
Okay, makes sense.
But in a superconductor, below a certain critical temperature, that resistance completely vanishes. An electric current can flow, theoretically, forever without losing any energy. It's perfect efficiency for electricity.
Wow. Okay, that's one. What's the other key property?
The other one is the Meissner effect. This is where the superconductor actively expels magnetic fields from its interior.
Expels them, like pushes them out.
Yeah, exactly. It becomes a perfect diamagnet. When it gets cold enough, it just won't allow a magnetic field inside it. And that's what causes that cool levitation effect you see. The magnet floats because the superconductor is pushing its field away.
Okay, zero resistance expels magnetic fields. Got it. But I read something recently, this Cornell group. They did something that sounds, well, frankly, nuts. They took an insulator and made it superconducting just by twisting it.
Ah, yes. That was fascinating work. It really shows how much we're still learning. They took the specific insulating material, laid it, and twisted the layers by just, I think it was 3.5 degrees.
Tiny twist.
A tiny twist. And that subtle change in structure, how the atoms lined up, was enough to completely change its electronic properties, and boom, it became superconducting.
Even though our current theories maybe don't fully explain why that specific twist works.
Exactly. It pushes the boundaries of our understanding. It shows that sometimes small structural tweaks can unlock really unexpected behavior.
Okay, so these materials have incredible properties. Let's talk potential. If we could harness these easily, what kind of world are we looking at? What are the big applications?
Oh, the potential is just huge. You could transform so many sectors. Take medicine, for instance, MRI machines. They already use superconducting magnets.
Right, for those detailed body scans.
Exactly. If we had better, easier to use superconductors, MRIs could become even more powerful, maybe cheaper, more accessible. Imagine better diagnostics available everywhere.
And energy. That seems like a massive one.
Absolutely massive. You could have superconducting magnetic energy storage, SMES making power grids way more stable and efficient, storing energy with almost no loss.
Okay.
And then there's transmission. Imagine power lines that carry electricity across continents with zero energy loss due to resistance. Think about the implications for efficiency, for sustainability. It would be revolutionary.
No more energy wasted as heat, just moving power around.
Wow.
And transportation. We always hear about levitating trains.
High-glove trains, yeah. They exist, but they're expensive and complex, partly because of the cooling needed for current superconductors. If we find room temperature or easier to cool ones, you could see ultra-efficient trains, maybe even other forms of transport, just gliding on magnetic fields.
What about science itself? You mentioned the gravimeter earlier.
Oh, definitely. Big science relies on them. Particle accelerators, like the Large Hadron Collider at CERN. They use incredibly powerful superconducting magnets to steer particle beams. We're talking massive cables carrying like 12,500 amps.
Whoa.
Without superconductors, those kinds of experiments just wouldn't be possible.
And I've seen mentions of other things too, like superconducting wind generators. More powerful magnets mean more electricity from the same wind.
That's the idea. There's been work on rotors using materials like Rapley CO for, say, a 3.6 megawatt generator. More power, potentially lighter generators. And then there's advanced computing things like the cryotron, a superconducting switch. Faster, more energy-efficient computers. Plus, super-sensitive detectors for light, for astronomy, or other fields. The list goes on.
Okay, so the promise is incredible, which brings us back to that question. If they're so great, why isn't everything running on superconductors already? What's the big roadblock?
Yeah, that's the crucial point, isn't it?
Yeah.
The roadblock is the conditions they need. We talk about high-temperature superconductors, but that term can be a bit misleading.
High compared to absolute zero, you mean? Not high like room temperature.
Exactly. While we've found materials that superconduct at temperatures that are, getting closer, maybe negatives 13 degrees Celsius, which is amazing progress,
But there's a catch.
there's a huge catch.
Yeah.
Achieving those high temperatures almost always requires absolutely crushing pressures, hundreds of gigapascals.
Hundreds. How much is that in like real terms?
It's millions of times the atmospheric pressure around us right now. Think pressure deep inside the Earth. You typically need specialized equipment, like diamond anvil cells, just to create it in the lab.
Okay, so totally impractical for, wiring up a city or putting in your phone.
Precisely. That's the main hurdle. We've seen amazing hydrides, compounds with hydrogen, like lanthanum hydride, yttrium hydride, even that carbonaceous sulfur hydride that hit room temperature.
Room temperature, that sounds like the goal.
It was room temperature superconductivity, 288 Kelvin,
Yeah.
but at 267 gigapascals. Just immense, immense pressure.
So the temperature's going up, which is good, but the pressure needed is still astronomical. That seems like the real bottleneck for actually using these things.
It absolutely is. Think about this. Researchers have computationally predicted thousands of potential superconductors. But how many have actually been made and confirmed in the labs?
Probably not that many.
Less than 1%. And the main reason is that extreme pressure requirement for synthesis and for the superconductivity itself, it's just incredibly difficult and expensive to work with.
Okay. So the dream is there, the roadblock is pressure. How do we get past it? This is where the AI comes in, right? Materials informatics.
Exactly. This is where we see a shift towards what some call the fourth paradigm of science, data-driven discovery, instead of just relying on intuition, theory, and slow trial and error.
Which sounds painstaking for materials.
Incredibly painstaking.
Yeah.
Now, we can use huge data sets of known materials and clever algorithms, AI and machine learning, to predict new materials with desired properties. It's like having a super-powered search engine for discovering materials.
Okay, tell me more about how that works for superconductors. I saw you flagged a paper by Tran D. Huan and colleagues.
Yes, their work, published by the American Chemical Society, is a great example of this in action. It's titled Superconductor Discovery in the Emerging Paradigm of Materials Informatics. They're really at the forefront, using AI to tackle this superconductor challenge from different angles.
What are those angles? How is AI helping?
Well, one way is just classification. Can AI look at the chemical formula or structure of a material and predict, is this likely to be a superconductor, yes or no?
Like a screening tool.
Pretty much. They use algorithms, like random forest, trained on known superconductors and non-superconductors. And the accuracy is impressive, around 92% correct for general classification.
92%, that's pretty good odds.
It really helps narrow down the possibilities. And they can even classify types of superconductors, like cuprates or iron-based ones, with even higher accuracy, up to maybe 96.5%.
Okay, so it can tell you if something might be a superconductor. Can it tell you how good a superconductor it might be, like the critical temperature?
Yes, that's the next step. Regression. Predicting the actual critical temperature, the TC value. They use different AI models for this, like neural networks, fully connected ones, convolutional neural networks that look at atomic arrangements.
And how well do those predictions work? Is it just a rough guess?
No, they're getting remarkably accurate. The best models show really high correlation with experimental results. R-squared values up around 0.9 or higher in some cases. The average error when predicting TC can be as low as, say, 4 Kelvin.
Only 4 degrees off. That's amazing. That must save researchers a ton of time, letting them focus on the most promising candidates first.
Absolutely. And this connects to the bigger picture. Using these predictive models to actively search for new materials. Tran D1 and the team use their models to screen massive databases, like the Inorganic Crystal Structure Database, ICSD.
Looking for needles in a haystack.
Exactly. And they found potential needles. They identified around 2,000 candidate materials predicted to have a TC above 20 Kelvin at ambient pressure.
Ambient pressure. Okay, that's the key. So not needing those crazy high pressures.
That's the goal. And what's really exciting is that among those 2,000, There was a smaller group, about 35 materials. They didn't look like any known families of high-temperature superconductors.
So the AI isn't just finding more of the same, it's pointing towards completely new possibilities.
That's the potential game changer, yes.
Huh.
It suggests new avenues of chemistry to explore. And it's not just theoretical. They mentioned Cambi-2, calcium bismuthide. A model predicted it, and it was later experimentally confirmed to be a superconductor.
Wow, so prediction leading directly to discovery. That's powerful.
It really is. And the models are also being designed specifically to tackle the pressure problem, trying to find materials that work at lower pressures.
How do they do that?
Well, for example, they used a multitask neural network to screen for elements like alkali and alkaline earth metals that might form hydrides superconducting closer to ambient conditions. One prediction was for RBH12, rubidium hydride, predicted to have a TC up to 126 Kelvin, but potentially at 100 gigapascals or maybe even less. Still high pressure, but a significant step down from the 200-plus GPa range we often see for other high-TC hydrides.
So the AI is helping chip away at that pressure barrier. That's incredibly promising.
Right.
But there have to be challenges, right? Limitations. AI isn't magic.
Oh, absolutely. A major one is that these models are, only as good as the data they're trained on. If your data set mostly contains superconductors found below, say, 150 Kelvin, the model might not be great at identifying something totally new with a much higher TC.
It only knows what it's seen before, basically.
Right. Its domain of applicability is limited by the training data. If it hasn't seen examples of superconductors working under very high pressure or certain types of chemical structures, it might miss them.
So what's the path forward then? We just need more data, better data.
That's a big part of it. Expanding the data sets, like the COMPAS-C database they mentioned, to include a wider variety of materials, especially non-hydrogen-based ones found under different conditions, is crucial. It helps the AI learn a broader range of patterns.
Feed the AI more diverse examples so it can make better, broader predictions.
Exactly. And then there are still fundamental challenges on the theory side, too. Our existing theories, like Migdal-Eliashberg theory, aren't always perfectly accurate for these complex materials. And predicting the precise atomic structure of a novel material, especially under pressure, is still really, really hard. It's a complex interplay.
So it's not just AI, but AI working alongside better experiments and maybe even new theoretical insights.
Precisely. It's a multi-pronged attack.
Okay, so recapping our journey today. We started with the truly mind-bending properties of superconductors, zero resistance, magnetic levitation, and their incredible potential to reshape everything from medicine to energy grids.
Then we hit the major roadblock, the extreme, often crushing pressures needed for many of the highest temperature superconductors discovered so far.
But then we saw how this new paradigm of materials informatics, powered by AI and machine learning, as highlighted by researchers like Trandy Huan, is offering a powerful new toolkit.
Right. AI models that can classify potential superconductors, predict their critical temperatures with surprising accuracy, and screen vast databases to accelerate discovery, even pointing towards candidates that might work at lower, more practical pressures.
It really feels like we're on the cusp of something significant here, even with the challenges of data limitations and theoretical hurdles.
We really are. And it leaves you with a fascinating thought to ponder. What if AI doesn't just speed up the discovery of materials like superconductors? What if it fundamentally changes how we understand matter itself?
How so?
Allowing us to eventually design and tailor materials from the atom up, achieving properties we can currently only dream about. Imagine that future. How profoundly will that reshape our world?
That's a powerful question to end on. Definitely something for you, our listeners, to think about.